Assalamu alaikum. Good afternoon. Can you hear my voice? Okay. During the last session, we start to talk about network security, and we start to talk about cryptography as one of the basics of network security tools. And we said that even if an attacker knows or a strategy or cryptography strategy, he or she can try to break or ciphertext. We talked about this a little, but let me continue the course with talking about symmetric key cryptography. What is symmetric cryptography? When we talked about cryptography, we have two different ideas. The first one is using a symmetric key for encrypting and decrypting text, plain text, for example. Excuse me. Right now, Yasser. Okay. So I'm repeating again. In your home, you have a key. Then you can go and create some other copy of your key. For example, you can have a key. You can get a key to your parents, your wife, your husband, your kids. Okay, you can give them their copies, so you can lock the door and they can unlock the door. This strategy is symmetric key strategy. In cryptography, we have a similar strategy. We have a symmetric key or K of S. So Alice can encrypt her plain text by the symmetric key, and the ciphertext encrypted by the symmetric key then can be sent over the network. At the receiver, the bomb can decrypt the key, can decrypt the ciphertext using the symmetric key again. Okay, he can decrypt the text and extract the plain text from the received message. So when we are talking about a symmetric key cryptography, it means that Bob and Alice use a shared key. There is one key, and Bob and Alice can have their copies of that key. So who is Bob and who is Alice? I don't know. Everyone who has the key can encrypt the message or can decrypt the message. This is the main problem with the symmetric key cryptography. Each person who has the key. And there is another question too. Okay, Bob and Alice are using a symmetric cryptography, but how they can agree with the key value? Their key must have a value, okay? So how they agree with the value of that key. How? Here we don't talk about the strategy of cryptography, basics of the algorithm, a specific algorithm, okay? We are talking generally, symmetric key cryptography. For example, we can have several techniques when we talk about cryptography. For example, when we talked about a symmetric key cryptography, we can use, for example, substitution ciphering. What is this? In this strategy, for example, here, look at this one. Here we have different characters, English characters, okay? And we then just we substitute those characters with someone else. Okay. For example, instead of A, we can use M. Instead of B, we can use N. Or for example, instead of Z, we can use Q. So if I have this plain text, Bob, I love you, Alice. Okay. According to this key here, this strategies for substitution, here, instead of B, I know that I should use N. So N, we have two B's, two B characters here. So I'm replacing those B with N. Instead of O, I should use K. So here, this O is replaced by K, here again, and here again. Instead of I, I'm replacing it with S. I-S. Instead of L, we are using G. Okay? Just substitute each character by a new one. How? Based on this strategy here. This is the key. This is all key for substitution, all key for encryption. We are replacing one character by another one. Here we have in English, we have a set of 6 different characters. Those characters are replaced by someone else in substitution ciphering, and this is the key. But this is said in this strategy can be breaked. We can break it very easy. How? For example, in English, I know that we are starting with. For example, this letter can be started with I. I is a single character, and so statistically, I can recover this. For example, I can replace I when I see S, I can replace it with I. Or I know that this message is sent between Bob and Alice. So NKN maybe is Bob, and MGSBC maybe is Alice. Maybe, I don't know. Okay. So if my idea about the substituted characters is correct, I can find those replaced characters, and I can continue this strategy. Okay. So this strategy can be breaked easily. We have another strategy. Instead of using one substitution key or one substitution ciphering, I can use n different substitution ciphers. We are showing them by M1, M2 until Mn, M of n, okay? And then I can use a cycling pattern here. I have n different patterns, okay? And then I can use a cycling pattern. What does it mean? For example, here, n is equal to 4. So it means I have 4 different patterns. And then for the first character, I'm using pattern M1. For the second character, I'm using pattern M3. For the third character, I'm using pattern M4. For the fourth one, M3. For the fifth one, M2. You know, for each character, I'm using a specific substitution cipher. And I know that that substitution cipher is different from the others. So, one by one, character by character, I'm using different strategies. And when we say that this pattern is cycling, it means that I'm continuing this strategy, M1, M3, M4, M3, M2, and again, M1, M3, M4, M3, M2. And we continue, we repeat this strategy. So we call it a cycling pattern. This pattern is recycled during the work. And for each character, I should find, okay, this character should be replaced by the ciphertext, for example, ciphertext X. Okay? So, if you use this strategy, its breaking is a little hard. So because for each character I'm using another characters. For example, let's see this example. We receive a word dog. Okay, this word has D, O, and G letters, characters, okay? According to this pattern, D, if I want to replace D, I should look for D in pattern M1. For O, I should look for O in pattern M3. And for G, I should look in pattern M4. Each pattern has a specific string of characters. I should look on those patterns and replace the word dog here. So this strategy is more sophisticated than using a single substitution cipher. There is another algorithm for encryption. Its name is DES, or Data Encryption Standard. This standard is used more than 3 decades, but in 1993, the NIST organization tried to standard this algorithm, the DES algorithm. The DES algorithm is using a 56-bit symmetry key and 64-bit plain text inputs. Okay. This strategy, the DES, is consists of 16 different steps. In each of those steps, we try to encrypt the message, encrypt, replace, and enhance the message during each of those 16 steps. Okay. But it's very interesting that this algorithm with 16 different steps. Those steps, if you look on inside this, you can see that in each step we have some shift to right or left. We have some XOR operation and several other operations during each of those steps. But today we know that the DES codes can be decrypted very easy in a few minutes. Why? What is the problem with this? The problem is that the DES uses small keys. Here we said that the symmetry key is 56-bit key. Is a 56-bit key. Okay, this length is too short for decryption. This key is very short. Why? I don't know why, but if you use brute force attacks, you can decrypt or break this encryption strategy very soon. Just in a few hours, maybe in a few minutes. Okay, Naima, I will answer your questions. Okay. So, how can I overcome this problem? We have another strategy. Comes from this. We call it triple DES. Triple DES means that I'm repeating the encryption of this strategy 3 times. So we have 3 56-bit keys. Wait a minute, I will in triple DES, we are using the DES mechanism, this strategy, this algorithm 3 times. So we can use 3 different keys because I'm using this triple times. So 3 times, so we can use 3 different keys, or maybe we can use 2 different keys. How? During the first step, I'm using, for example, key number 1. In the second round, I'm using key number 2, and in the third round, I'm using key number 1. So in triple DES, we need 3 different keys, but we can reduce them into 2 different keys. But generally speaking, in this case, we are using 3 keys with 168 bits. So triple this is very strong. If I compare it with, for example, this, we can break this easily, but in triple this, we cannot break it easily. But after the weakness of this, in the USA, another encryption standard has been proposed. Its name is AES, or Advanced Encryption Standard. This standard is proposed in November 2001 by the NIST organization, again, NIST. To replace this strategy. The AES standard is using blocks of data with 128-bit length, and in this standard, I can use the keys with 128, 192, or 256-bit length. So you can see, comparing with this, in AES we are using larger keys. Using larger keys means means that AES is stronger than this strategy. To compare this this strength, I can use, for example, I can say that, for example, let's suppose that I am decrypting the texts which are encrypted with this in 1 second. It means that I'm spending 1 second to decrypt this encrypted text. If I spend only 1 second, in this case, only 1 second to find the encrypted message in this, with similar specifications in our computing platforms, we should spend 149 trillion of years to decrypt AES messages, AES encrypted messages. It's very good. This is strong, but we know that this strong algorithm can be replaced very easily. They can be break easily. But here we can see that if this needs only 1 second to decrypt the message, for AES we need 149 trillion dollars, trillion years to decrypt the texts which are encrypted by AES. This shows the strength and the amount of strength in AES strategy. Okay. Yes. By using brute force attacks, we can decrypt these messages, these encrypted messages, very easily. But in comparison, we okay. Okay. As I said, when we talked about encryption, we have two different strategies. The first one is using symmetric keys, but the main question is this: how we can share that key? Because we know that if someone else receives that key, he or she can enter the sending software. It's it's an important problem. How can I replace? How can I manage? How can I use those strategies? Because I should send the keys over the internet, mostly. So someone else can sniff the packets to find the keys. Okay? Is there any solution to solve this problem? We should say yes. There is a powerful solution for this problem. We call it public key cryptography. In public key cryptography, we have two keys, a public key and a private key. When we talked about a public key, this key is scattered around the world inside different networks. You can find it easily. The other key is private key. Although the public key can be accessible via the internet, can be used by different clients. In private key, I know that the private key is in my pocket. I never shared the private key, so they cannot. Nobody can know that key. Okay. Maybe someone asks me, okay, what is the benefit of using two different keys, a public and a private keys? What is the difference between them? What is the point of this strategy here? Let me show you the public key cryptography here. Here you can see this plus L minus signs here in the keys on top of the head of up. When Alice tried to send a plain text to Bob, he or she have to encrypt the data. But how? Look at this one here. The plain text message M is encrypted by the public key of Bob here. Okay. So the Alice find the public key of Bob, and as I said, this key is distributed over the internet, so everyone can access to this key. Okay? But what about the other key? The encrypted message arrives to Bob. To extract the message, Bob have used its private key. I said that this key is in Bob's pocket. Okay? So Bob tries to decrypt the cipher, the arrived ciphertext with his private key. Look at this one here. This is M, K plus M, K plus of B. And finally we receive the plain text here. Okay. The main point here is this one here. Here and in the next slide here, get this one here. When I'm encrypted by one of those keys, I have to decrypt it with the public one. Encrypting with the public one, decrypting by the private one. It's not important which of them we use, which of them. But the main question is this. If I encrypt a message by one of those keys, I have to decrypt it by the other key. This is the basic of public key algorithms. The first public key encryption algorithm is proposed by RSA, Rivest, Shamir, and Adelson algorithm. Okay, let me stop the course here. If you have any question, please ask me, answer, and after that I will be back to the course. Okay? Okay, let me go back to the course, to the lecture. The basics of RSA. RSA is the first public key encryption strategy in the world, and it's based on some mathematics. You can see them here, and this one here. Okay, look at this formula here. A mod of n in power of d mod of n. Mod is the reminder function. Let's suppose that x is 14, n is 10, and d is 2. Okay? Let's replace this information here into the main equation here. X mod of n in power of d mod of n equals to 4 in power of 2 mod of 10, which is equal to 6. And x of d here is 14 in power of 2 equal to 196, and x of d mod of n equal to 6. Let me focus on RSA and talk about RSA and find how an RSA works with an example here. Let's suppose that I have this message 100100001. I want to send information to this one. This is this character here, this number here is equal to 145. The message is presented in binary and in decimal. The value of the message is 145. And in an example, I want to show you how RSA works. Let's suppose that we have that message, and now I want to find different values. Firstly, I should find P and Q. They are prime numbers. Prime means that I cannot divide them into smaller parts. For example, 5 is prime, 7 is prime, but 8 is not prime. Okay, because 8, I can divide 8 into 2 and 4. 2 times 4 is equal to 8. Okay. So firstly, I'm choosing P and Q as two prime numbers. And let's suppose those P and Q as much as large as much as possible. For example, each of those value can have size of 10 to the 4 bits. Okay. And we compute n as P times in Q and Z as P minus 1 times in Q minus 1. Okay, and after that, I'm choosing E is smaller than N, where E has not a common factor with Z. We calculate Z here. So E must be chosen, must have a smaller value, smaller less than N. And E and Z, I'm choosing E is smaller than N, and E and Z must be relatively prime. It means that E and Z, I cannot, for example, divide Z by E or divide E by Z. Okay? Because it's prime, relatively prime. Then we choose a D such that ED minus 1 is exactly visible by Y. If you find those parameters N, E, P, Q, E, D, and so on, I can say that my public key is this, N and E. And my private key is this, N and D. This is the primary message. We call it so here the public key is N and E, and the private key is N and D. And we can prove it. Look at this one here. We can prove it. Let me show you an example. Let's suppose that P is 5, Q is 7, and N using creation here. I'm continuing these steps. So n is 5 times 7, that's 2, and z is N is 35 and Z is 24. And we can find E as 5 because I said that we should choose it. So E is 5 and D is 29. And as I said, N and E is the public key and N and D is the primary key, is the private key. So simply I can apply them. So this one here, the big pattern is this, and the length of this pattern is the value of this pattern is 12. M in power of D is 2488. This one here. And I want to find C. C is equal to M in power of E. And as I note, C should enhance by the power of D. And finally, find the mode of N. During this process, you can see here, when I'm trying to calculate C in power of D, you can find that the output of this one here, C in power of D, you can see this number is too large. We cannot simply accept this large number into a variable in computers because this value is too large. This is the big problem of RSA. When we try to do that, this step is too heavy. Okay? So, here you can find why RSA works. It's not important for me. And the other one here, I said that it's not important. You're starting from with which of those encryption types. K minus 1 in parentheses. There's no difference between them. M is encrypted by the public one and then decrypted by the private one, or here it's not important. I'm applying the public key over the private key. This one here, that is very interesting. Okay. Let's see, check something. Okay. Okay. The RSA is secure when I compare it with, for example, this. RSA is secure. Why? Because in RSA, I'm using a public and a private key. I'm publishing my public key over the internet. The other parties, the other people who send me information, they should learn my public key. And just me, just I can re-extract or decrypt the message by the private key. It means that a person can decrypt these messages, the messages encrypted by RSA, only the person who encrypted it. Maybe someone asks me, okay, is it possible to find P and Q, or knowing, for example, N? Yes, we can find P and Q to decrypt it, to crack the uh, structure of RSA. Okay, we can crack it, but it's not easy. Because the architecture of RSA is complicated. So RSA is secured. I cannot guess the parameters, different parameters in RSA. But RSA suffers from a big disadvantage. The cost of RSA, computational cost of RSA, is very high. The disk is at least 100 times faster than RSA. So RSA is too heavy. That is interesting. RSA is too heavy. So we have two different strategies. The symmetric key strategy. In symmetric key, we are using a shared key between the sender and receiver. The shared key, the symmetric key is uh, easy, and its problem is with the sharing the symmetric key. How can I announce my key value to the other side? This is a big problem with the shared key. If Trudy stands and catch that value, Trudy can extract my messages, can decrypt my messages. Okay, but in RSA we have not this problem. But the problem with RSA is its high computational overhead. So what is the solution? Why should I do? One of them is complex with high level of computational overheads, and the other one has a problem with its key distribution. The solution is easy. During the first steps of setting the connection between Alice and Bob, they can start with RSA. So Alice and Bob starts with RSA. Start their stations with RSA. But after that, we can send that shared key, a shared key, over that RSA connection. I'm sending the shared key over that RSA connection. And so we can see that after those transmission, sending the symmetry key to the other side, I can forget the RSA communication and continue with, for example, AES or something like that, which is symmetric one. So during the first phase, I'm using RSA, but after that, I'm using AES or some other methods to have access to the information. This is the best solution, sending the symmetry key to the other side over a public key strategy, public key algorithms. So simply, you can send session keys for other main information using this strategy. Okay? And after that, after sending those information, we can start to send information directly using a symmetry key. Okay? Oh, the time is over. Any question? Naima, take a break, yes. Or today's lecture is finished right now. The chapter 8 is the last chapter. No. No. After this chapter, we will go back to chapter 5. Chapter 6, excuse me. Chapter 6. We have some contents in chapter 6. Firstly, I decided to cover those chapters that I want to talk about them completely. Teach the whole of those chapters. And after that, we go back to some other chapters. Some parts of other chapters, okay? Okay, I wish the best for you. Have a good day and bye.